Hello.
Hey, can you hear me?
Yes, I can hear you. Hope you're doing
Awesome.
good. How's your day going?
Pretty good. How about yourself?
So far so good. Cannot complain. It's cold in Seattle, but isn't it always? But yeah.
Yeah,
All right.
awesome.
So maybe give me a quick run through of what you're prepping for, as well as what you're looking to get out of this before we get started.
Yeah, so I have a coding, I guess, screening coming up at Microsoft.
Mm-hmm.
And I just found out today it's actually a level 63 position in one of the software reliability engineering teams. And so I don't
Mm-hmm.
really know if that would be a different type of assessment than a standard engineering assessment. I have a background more in the infrastructure side and not really on the software development side, and so I'm a bit nervous if this is just going to be, like a leak code kind of situation. Um, but that's really all I know is that it's going to be, the standard technical screen as far as I understand.
I see. Okay. Oh, so it's L63. Sorry, I came in with my collection of junior questions because it was indicated that this was a junior interview. So, okay, let me get my understanding straight. So it's L63, which is senior, I believe, right?
Yeah.
I see. Oh, crap. I wish I had prepped better because I don't have a collection of questions for senior SRE here. Let me
Okay.
check. Yeah, I really okay. I'll be frank with you. I don't think I'm too familiar with the SRE process, and so honestly, I was thinking it was going to be a SWE interview, and so I'm not
Well,
really sure if.
and and
Uh-huh.
and that's fine. We can do that.
Mhm,
As I said, I don't believe it's any different, but I don't know,
mhm.
right? And so,
Makes sense. Yeah.
and then I have another one coming up on Friday with Shopify, and this one's supposed to be similar like senior infra role,
Mhm.
but again, they have a requirement to do a pair programming exercise. Um, and
I
so,
see.
and so really like just uh, just give me something just to kind of like give me an idea of what I'm doing. If I'm like failing
Mhm.
miserably, then it gives me at least a gauge on where
Makes
I'm
sense.
at.
Yeah. Totally fine. Okay, so I'll just make sure I also adjust my metrics because for context, I think you might know that the coding interview typically will be the same across levels, only the expectations will be different.
Okay.
And so in similar regard, assuming it's a Leetcode style question, I would expect it to basically be standardized. The only thing that I'll have is high expectations of you. So with a junior, for instance, I would expect that they show me they can think through solutions. They don't have to necessarily do testing or think through all those cases. But given that this is L63, there's some extra considerations I'll be looking for in terms of optimality, speed of a solution, communication, of which so far you started strongly, and testing. So those are the bits I'll be looking for basically, just to adjust the heuristics there. But if you're comfortable, feel free to select the language you want to use, and I'll basically provide a question for you.
All right.
Perfect. So Python, good choice.
Ruby, sorry.
Oh, okay. Shoot. This looks very much like Python. Okay.
It really does, yeah.
Yeah. All right. So this is what we have here. So you're given a zero indexed 2D integer array of size 3 by 3. And
hmm
what this does, I don't know if you played that game where it's kind of like a bunch of numbers and you have to organize them. The only difference is in this case, you might have some cells that have zero elements. And our requirement in this case is we swap the rocks around. And so I'll give you an example with this one. So okay, can you give me a second? My son
Yeah,
kind of woke up. Yeah, but
no
go
problem.
through this and then I'll be back in a few, okay?
Sure.
Sorry, okay. He's been saved, so he is
Okay,
good.
great.
All right. So if we look at this, for instance, the one that you have here is zero, which means for us to actually spread all the rocks out correctly, we'll have to pick one from any of them really. Like we can, assuming we had one here, we can pick from that, but it's really up to us.
Mhm.
But here, because this is the only one that has extra rocks, we pick one from it, and we can either go 1, 2, 3 and put it there, so that one rock from the two, or we can go 1, 2, 3. And this is to say that the minimum number of swaps we have to spread the rocks out here will be 3. So
Okay.
mean swaps equals to 3. If we cannot perform any swaps, return -1. Right?
Okay.
So that is if it's impossible to spread out. So return -1.
All right. And so if I'm understanding this correctly, I'm just
Mhm.
going to write in my own words if that's okay.
Sure.
Uh, so I receive in a two-dimensional array 3 by 3,
Uh-huh.
and is it just one uh, of the values represents an uh, empty block, or can there be
Uh,
multiple?
that's an excellent question. There can be multiple zeros.
Okay.
So there can be multiple sections that
Okay.
need rocks. Yeah.
Values that signify needing a block are 0. Values that are non-zero signify that n number of blocks exist. And I'm assuming that if there's just one block and I move it, then that becomes a 0. And so that's not an acceptable solution.
Exactly. So for a spread to be considered, or at least in this case, for us to have considered the system as being solved, we need to have at least one stone within the cells.
Got it. So all stones need greater than or equal to 1 stones in each cell. If all values are not greater than or equal to 1, then return -1. If
Mm-hmm.
all values are greater than or equal to 1, then return number of moves needed to accomplish task. Um, and each move is a single adjacent cell. Is that correct?
Yeah.
So,
So
okay.
yep.
So 2 goes up, 1 goes up, 1 goes over 1. And so that becomes a 1. And so when I'm moving everything, so it starts as this, and then it will become this, and then it will become this, and then it will become this. Is that correct?
Precisely.
Okay.
That is very correct. Yep. You
And
understood
so
that correctly.
I plus equals 1, I plus equals 1, I plus equals 1, and then return I. All right. Um, okay. And so now this is this something where we shouldn't assume that it's always just going to be size 3, 3, because what if it's a 5 by 5, or what if it's non square, so it's rectangular, and so need to be careful here to not assume that 3 by 3 is the only way to do this. Is that a fair assumption?
By line two, it's fair to assume that we only need to deal with 3 by 3 in this case. That
Okay.
said, if you can design a more generalized solution, I'll be very impressed. That would actually be one of the things I look for in an L63 person.
Okay. All right. So let's then perhaps first solve for the 3 by 3, and then we can work on figuring out how to make it more generic. And
Okay.
so the first thing I guess we need to have is uh, just a way to test. And so um, we will say get moves, and then input our uh, matrix. Okay, and so get moves of matrix uh, equals 3. So that is what we want to do, and so we will do get moves, and we'll do a test that fails. We say add another 0 here, and so this will be -1. And so we want get moves of matrix.
Mm-hmm.
All right. So I received this, and let's assume for right now it is 3 by 3. And so the first thing that I'm going to do is I'm going to now, I guess that we need to worry about any space and size considerations. Are there any constraints or preferences here? Is this something that's I should be more concerned with the space, and so I need to perhaps use, you know, non um, non-dynamic uh, variables, so like not using arrays or hash maps or whatever, or is this something where I need to be much more careful with the time complexity and just try not to do uh, O of n squared, for example, like nested loops.
I'll give you the flexibility to approach it however you would, so long as it's optimal. To be clear, the core goal for me is to one, see that you can code, two,
Mhm.
see that you can think through optimizations. And
Mhm.
here's actually a neat trick about, it's not just Microsoft, but a lot of other companies. It's not necessary that you even solve the question optimally. Rather, they'll want to see that you can optimize the solution. So even if you don't have the most optimal approach, if you can optimize even one section or two sections of your code, typically that's a good sign. And
Okay.
if you can also analyze the complexity correctly, that's usually in your favor. So in this case, choose any approach that makes sense to you, and then hopefully you can optimize it even further if it's not optimal.
Okay. All right. And so again, then let's move forward with attempting to solve this. So I need to first understand how many empty squares there are and how many extra uh, extra blocks or stones I have, because
Mhm.
that's a quick way to understand if uh, we can even solve this problem. And so that can be a quick fail if it doesn't already exist. And so I will uh, do a matrix oh, uh, total um, stones, equals matrix dot flatten dot sum. And so that will give me the total amount of stones that are in this matrix. And just note here is that it is an array operation looping through all the arrays to get the sum. So this is already a 0n operation in itself.
That's good.
So next, I have the total stones. I'm not going to, for now, I'm just not going to assume it's 9, and so I'll just, uh, do a pre-optimization. Hopefully, I don't get in trouble for that, but I will
Mm-hmm.
do num stones, or num squares equals matrix dot flatten dot length. Oh, that yes, that's right. And again, an operation. Now, I have an idea to optimize this in the future. Is that perhaps I could run join these two operations into one and run a map, run each map matrix to combine getting squares. Okay. So now I have the total number of stones and the total number of squares. And so if num squares is greater than total stones, I'm just going
Mm-hmm.
to return a -1, because this means that this is an impossible puzzle to fill all squares with given stones. All right. Uh, and so now I should have. How do I run? Oh, run. There we go.
I would say not to worry too much about running, but if it helps you with debugging, that's totally okay. Like I'm also interested in the general approach, but if it helps debugging, that's totally fine.
Oh, okay. Yeah, I was just trying to see if this was actually going to do something. Um, or like, am I supposed to name it like a main function or something? Like,
Let's see. We've called matrix here, and it's not. Do we print anything? I don't know how we
okay, yep.
actually. Yeah.
All right, yep, there we go. Uh, yeah, so that's what I need. Uh, yep, all right, so -1. Great. All right. Um, Now I have to understand that, okay, I have all of my squares available, and so
Mm-hmm.
now I need to move. And so I will find the coordinates of the zeros, and then I will find coordinates of non-zeros. The minimum number of moves required to place one stone in the cell. Now this one is going to be a bit inefficient because I'll need to understand a lot of different possibilities.
Mm-hmm.
Okay, the minimum number of moves. All right. So first I will have a empty um, squares array and an available squares
Mm-hmm.
array. And so I'm going to use these to track which are the areas that I need to move to and which are the areas that need the that have the available stones. Available
Mm-hmm.
stones. All right. And so now I will do a matrix. No. Uh, uh, 0 to matrix dot length each I, and then a row equals matrix I, and then 0 to row dot length each to j, and I will. Oh, thank you. Column if uh, row j equals 0, then I will do empty squares ij. If row j greater than 1, then I will do available stones, the location, and the number that is available. And so now I have where the stones need to go, and I have where the available stones are. Okay. Now uh, let's do some back of the napkin math here. So if I know that empty square, let's just assume it's a single array, is uh, 0, 2, and I know
Mm-hmm.
that available stones equals uh, 2, 1, the number is 2, then what I can do is I will, so uh, 2 minus 0 equals 2, and 2 minus, I'll do 1 minus 2, absolute value equals 1, and then 2 plus 1 equals 3. And so I know that moving this to the empty square is
Mm-hmm.
3 moves. And so for 1, I can do that. All right. And so,
Just out of curiosity, so that's on the basis of it being right here, right?
mhm.
So on line 27, what if I had another one right here?
If you had one right there,
Mm-hmm.
okay. And so that math would be empty square would be 0, 2, and then the available stone would be at 0, 0,
Mm-hmm.
and the value is 2, and so that would just be 0 minus 0 equals 0, and a 0 minus 2, and absolute value equals 2, so moves equals 2. Um, and so because of that, so let's just make another test for that while we're doing this. And so now what I need to do is that for each uh, available square,
Yeah, I'm hoping you can still hear me. I kind
yes,
of got dropped for a second. Okay.
yep, no
Oh, so
problem.
just to do a quick recap here. So what did we say about the case where we have like two stones in the origin cell?
So
So
I did the math, and so the math would still be the same. That if it's here, then this would be coordinate 0, 0, and this is
all
coordinate
right.
0, 2, and so 0 minus 0 for
Mm-hmm.
the x-axis is still 0, and 0 minus 2 absolute value is 2, and so it would be 2 moves.
Excellent. So you're using the absolute distances. It's essentially not Euclidean distance, the Manhattan distance. So you're evaluating the differences in x and the differences in y in absolute terms, and that's basically your distance, right?
Yes.
Excellent work. Okay, that makes sense.
And so here, for now, here's the inefficient part to, because it's easy to solve, but it's more difficult
Mm-hmm.
to solve for minimum number of moves. But let's solve this so we have at least something working. And so available squares dot each, and then I will have or empty squares dot each, not available squares,
Mm-hmm.
and then available stones dot each. Alright. And so I will total moves equals 0, and then return total moves. So now I'm going to just do some math and say, yes, 0, yes, S 0. Um, I'm missing a variable here.
All right. Feel free to diagnose it. That's totally okay. And I know I'm very hands off. Full context. That's basically how they will evaluate it at L63. They want to see how you even unstick yourself, basically.
Yep. Yeah. And so basically what I need to get to the total moves, but because I'm iterating through this loop multiple times, I need to see which one of these stones is the most optimal stone to move for each
Hmm.
square. Um,
Exactly.
and so that's why I'm saying like I just need to get the appropriate number of static variables here, or not static, but variables here, so that I can
Hmm.
make sure that I'm not overwriting values that I may need in the future. Um,
All right. So maybe I have a quick question here. So say we have multiple, we call it, say we have multiple stones that really require filling, right? So we've
mhm.
kind of identified that we could have multiple empty cells. Can we maybe, like take a step back and try and generalize the heuristic? Like, how would we know which particular cell should feed a particular stone or a particular empty cell? Like, of the many cells we have that have more than one stone.
Yeah. Okay. And so and so what I need is I need to understand which cell has the least amount of moves
Hmm.
to fill each empty cell. Would
Exactly.
but I also need to track which cell has been decremented so that
Hmm.
I'm not turning that cell into a zero. So, like let's say that if a cell somewhere in the middle had, 5 and all of these were zeros, then that cell would be left with 0. And so that's something that, we uh, can't allow. And so, yeah, and so we definitely need
Exactly.
to have a few more arrays here. And so we would have,
Is there, just out of curiosity, what algorithm will that be? So, say I start from a cell, like let's think of a cell, XY, and
mhm.
I want to see which of the cells near me or which of the cells closest to me can potentially donate a rock to me or a stone to me. Do you know of any algorithms that will be suitable for this?
I I don't know. Like I
All right.
don't,
So
yeah, I don't have the glossary of terms.
all right, let's rephrase that a bit. Yeah. And so if I was to, let's say, start from my current cell, like let's
Mhm.
think of this particular cell, let's say XY,
Mhm.
which are the cells I can move to in one move? Or which particular cells can I visit with just one move?
Oh, it would be x plus 1 or y plus 1.
Exactly. So there are four cells, we call it the von Neumann neighborhood in our case, but
Mhm.
that basically is following the Manhattan distances. I don't know if you know that term. So, there's some types of distances. So there's a von Neumann.
Mhm.
You don't have to use these technical terms in the interview, but, in your case, I'm going to give it to you because I feel like if you just throw this in an interview, typically it stands out. There is another type of distance called Moore distance. So what you just described is referred to as the von Neumann distance, and you can look them up. Not distance, neighborhood. You can look them up if you want to
Mhm.
verify this.
Okay.
So now, with this in mind, you familiar? Oh, neighborhood. Okay, damn, that's a long word. Okay, so are you familiar with BFS and DFS?
Uh, no, I'm not.
So okay, so this is concept one. So let's just break it down a bit further here. So this is neighborhood types. The second thing we are thinking about here is BFS and DFS. This stands for breadth first search, and the second one is depth first search. Have you heard of these
Mhm.
two terms before?
No.
All right. So, as the name suggests, really, for breadth first search, you're looking at the breadth. So if I stand right here, or if I stand on one particular spot, who are my nearest neighbors? And then if I go to those neighbors, who are their nearest neighbors? And you are considering all the neighbors really. So on any particular cell, if I was to look at, let's say, this cell here, cell 02,
Mhm.
then its neighbors are cell 01 and the one below, going by the von Neumann neighborhood. If I was to go by the Moore neighborhood, then it will be cell 0 here, cell to the left, the cell below it, and the cell diagonal to it. If it
Mhm.
was the center cell, like I think it's better. Let's look at example 20, on line 25. So I think that's a better one to use. So if I was considering just this middle cell,
Yeah.
for the more neighborhood, all the cells are actually its neighbors. So if I was just at that particular cell, I can access all other cells with one move, going by the more neighborhood. In our case, though, we care about the von Neumann neighborhood. So the only cells that are my neighbors by BFS, by breadth first search, those are the ones above me, right below me, to my left, and to my right. And
Mhm.
they use the formula that you described, plus 1y plus 1x minus 1y minus 1x, right?
Mhm.
And so the reason I'm mentioning this to you is because in this case, if I was to just, find the collection of empty cells, the cells that need a donation, and I immediately start doing a BFS, a breadth first search, then I can immediately start scanning for cells that can potentially donate to me.
Mhm.
You see where I'm going?
Yeah.
Yeah. And so if I just did one scan, then I see, okay, one, this one, this one. Actually, because it's a von Neumann, so one scan, it's this cell here and this cell here. And then two scans, the middle cell, the one here, and the one below, and this one here. So immediately I know that this cell right here, by the second move, by the second level by BFS, this cell here should be able to donate to me.
Okay.
But in this case, that's one BFS move. What if I have multiple cells? That's kind
Right.
of the big challenge here, right? And
Right.
what if those cells need some sort of optimization?
Right.
Now that's where you think of multiple searches. Like, can you launch a simultaneous multiple search and then optimize for some form of shortest path? Like, which of the moves that we are deliberating can we use to minimize how many total moves I have to make while doing this neighborhood search? So that's
Right.
kind of the trick. And yeah, in your case, I can tell you're literally doing the same thing, only that you're approaching it from a more intuitive point of view and less of a, you know, traditional algorithmic person who's been dealing with this stuff forever kind of view, which I actually like. I like seeing people with that intuition because to me, at least, that shows more intellect rather than a person who's basically, you know, jammed Leetcode in their head. But okay, given all of this, I don't know if you have any more ideas, and we can proceed to try and solve it. Just take over, given what I've told you, and see if it can help you in any way.
Yeah. Yeah. Just I think where I'm stuck is
Hmm.
um trying to determine the shortest distance without resulting in the value becoming negative, right? So I'm thinking of a
Hmm.
use case where, uh, you know, I have something like this.
Hmm.
And so on line 25, I changed the middle one to a zero. And so
Hmm.
if I did just a naive search, I would
Hmm.
take both from here and be left with zero here and left with two here. And so I need a way to make sure that I'm tracking how many stones in each iteration have been taken because that searching for the nearest one isn't going to always result in the correct answer if I don't account for that.
That's an excellent point. And this is where I can maybe throw this at you. And, for context, this is exactly why I constrained it to 3 by 3.
Mhm.
So if you were to ask yourself this particular question, if I was to collect all the cells that are empty and collect all the cells that can donate, right?
Mhm.
Or even being simpler, how all the donatable stones basically. So that's the second question. So we need to collect all the cells that are empty and all the donatable cells, right?
Mhm.
Then for each cell, we also have a sense of the distance to pretty much all the other cells. So in essence, we are asking for what combination of donor and recipient cell, or what combination of all of them will actually give us the minimum moves. And the minimum moves can be computed by the approach that you use, the Manhattan distance. And so think of it from this perspective. One, we have a collection of all empty cells. This is, uh, you know, scan one. Let's say on scan one, let's just actually write all of this here. Scan one, collection of all empty cells. And then scan two, this is collection of all donor donor cells.
Mhm.
And I'll point something out. You don't even have to think of each cell just because it has two or three. You can actually log it in 2 or 3 times because it can donate to multiple cells. So in this case, this one cell can donate here, right? Assuming it was three, that is. Assuming
Right.
it was three, it can donate here and it can also donate here. Now, if you were to record this, in my case, what I can do is just say this cell has three representations. So I know I have, or in this case, there are two extra cells or two extra stones it can donate. So I can just say that. So
Mhm.
this cell has two possible entries. So it's almost like a lottery. Can I pick from it twice, or
Right.
can I pick from it once? So I can think of it from that perspective. Now with that, this is all donor cells, all empty cells. Fortunately, this will just be a singleton, or at least in this case, it will only have one. Now, the third question is I need matches, or I don't know how to refer to them. Is it permutations or combinations? It's actually combinations. So we need combinations of donor, donor and empty cells. And the core goal for us is to minimize total Manhattan distance. The Manhattan distance, by the way, is exactly what you're saying. So this is just you know, distance along not more, von Neumann neighborhood. The opposite distance that considers diagonals is actually called the Euclidean distance. So you can
Okay.
also use that. It's really up to you. So this is kind of the general question we're asking yourself. So if I was to pick this cell and another one in the empty cell. So let's say here I have, let's say, X. I'll say E1 or EX1, EY1. So this is empty, right? And
Mhm.
then this is, just copy this. Let's call this that. EY1, and this is EX2, EY2. So say those are our empty cells and those are our donor cells. And then in this regard, you can even generalize this further. Then we say this is DX1, DX2, donor X1, donor Y1, right? And we can
Yep.
repeat that. Say this is donor X2, donor Y2. We
Mhm.
can generalize this to EX. Let's say N2, EYN, same case, XN, YN. All right, so with this in mind, what we're looking for are combinations. So what kind of pairings you can achieve? And this has to be pairings, and this is something to note. All of these cells here must be paired to at least one of the cells here.
Right.
So we know that's one thing we need to look out for. So all empty cells must be paired to at least one donor cell. That's one thing we know. I don't know why it keeps auto
Yeah.
completing that way. So really, at a minimum, so let's go, stupid simple. What I can do is simply try and randomly assign them. So just make sure you're generating unique combinations of a cell here and a cell here. So it's literally this combination, this.
Yeah.
Alternatively, I can also generate combinations or permutations of all the cells here. So I can literally just generate all possible permutations of what size? Of size, let's call this K. Let's call this size here K.
Mhm.
So we can generate all possible permutations. And, in that regard, let's actually say this is K. I can generate all possible permutations, so palms of size K, and evaluate their distance. So once I generate all the permutations of size K, I can evaluate their pairwise distance to each of the cells here,
Right.
right? Do you see where
Yep.
I'm going with that?
Yep.
Yeah, and that can be my basis. So if I find any cells that, or if I find a combination that minimizes the total distance, that's the combination I need to go with, or that's the result I need to go with. Now, the tricky part, as you can tell, permutations are expensive to compute.
Yeah.
And it will almost be obvious when a permutation just doesn't work. And that's
Mhm.
where DP can come in. You can easily prune the tree because when generating permutations, you're basically branching out. And the BFS approach I told you about, that's the branching out. So sometimes you'll realize that there is simply a better move I can take, or if I've seen a better move before, then I know I don't really need to recompute. Like as soon as I know a distance has been exceeded and it's bigger than the minimum I've seen so far, I don't need to consider it again.
Mhm.
And so this is where they're pruning techniques. So considerations to think about here: you you can prune the search tree. So this is when generating permutations. Does this make sense?
Yeah. Yeah. But
Mm-hmm.
uh, so when you say prune the search tree, would that be um this kind of collective where you're doing effectively, there would be, if this is K and this
Mm-hmm.
is D for donor, you're actually creating a data set of K times D in size. And so is that what you mean that you're going to prune that tree, KD tree, or array, of all of the distances?
Now, by pruning the tree, I'm referring to strategies that we can use to avoid going down a rabbit hole when computing distances. And an example here of pruning. So there are multiple strategies you can use to prune.
Yeah.
In full context, pruning, even right from the word itself, by definition is it's the process of cutting branches on a tree, right?
Yeah.
So like as a coffee farmer or something, you go cut the branches of dead branches, stuff that you don't want taking resources from your main tree. Now in our case, we know for sure that there are paths we will not want to explore, mainly because they're just not better than anything we've seen so far. So let's say we've started the permutation scan and immediately we find a distance X. Then we evaluate that distance and that distance is, let's say, 15. Then we start, uh, you know, evaluating the running sum. So, we go to another permutation, we're starting to evaluate the running sum. We realize that for this particular sum, it's already at, let's say 15, even when we're halfway through the computation. At that point, we immediately tell ourselves, yeah, it's never going to be helpful. So we immediately skip that,
Right.
right? So that could be one way. That's an example of, not exploring, in this case, that's one strategy, not exploring permutations with a larger and mean uh, sum, or mean so far sum. That's one optimization. I'll be frank with you, there are so many such optimizations we can use, and it's really up to us to define how we want to generalize that. But at the end of the day, this is one of them I can think about. At the end, if you once you start solving the question, you'll actually see more solutions.
You're
And
right.
I'll do this because I really want to see you solve this. So I'll give you some code to go with. I know this is Ruby, which I'll admit I don't know much of Ruby, but I'll give you some starter code here, and you can use it. So give me 1 second. So I'm just asking ChatGPT to provide us some template code that we can use this.
No
I'm not
problem.
gonna lie, I also use ChatGPT. Yeah, so I'm hoping
Yeah,
this
no,
will
it's
help
great,
us
man.
here. Yeah. So this is like some helper code. Feel free to use it. I know the permutation ones can be a bit tricky, but feel free to use this above. So we know their coordinates pretty much, and this is size k. We know it's the size of the empty cells we need to work with. I know you can scan for the empty cells. Now it's your job to build the list of the other cells, the main cells. So build the list and then use this kind of function to get those size k, size k permutations, and then from there use that to actually evaluate those distances. All right. So
Okay.
I'll throw this in here. Feel free to use it.
Coordinates dot permutations.
Yeah, and if you wanna try to just print it just to see how they look like, you can also do that.
Yep. Permutation of coordinates. Yeah. Sorry, I'm just trying to
Hmm.
understand what.
Like, feel free to print it. Like, if you want, just try and print it, and then we can go through it line by line just to
Yep.
understand how it helps us with the solution. All right. So what has that done? So we have this collection of 1, 2, 2, 3, 3, 4, 4, 5.
Mhm.
But what it's giving us is tuples of 1, 2, 2, 3, 1, 2,
Mhm.
3, 4, 1, 2, 4, 5. So it's
Oh, I see.
combinations of size 2. So in similar regard, if you build the collection of donor cells, so just go in and retrieve all the coordinates of the donor cells, and then generate size k permutations. And by permutations here, we're just looking for different orders, right?
Mhm.
Because order matters with permutations. Then generate the permutations of whatever donor cells you have. Now, what that gives you is, and mind you, size k is actually the total number of empty cells. But that's the only bit that we're
Oh,
interested
got
in.
it.
But
Okay.
yeah, yeah. So what that gives you is one, a static list of empty cells, possible places that you can borrow, and then it's up to you to test which of the borrowing patterns gives me the best results. That's literally what we'll be looking for here. So I was going to say at this stage, so let's see. So right here, within this loop here,
Mhm.
what you're looking for is empty squares and available stones.
Yep.
So as soon as the loops are done, you have two things. You have a collection of empty squares or empty cells, I'm assuming, right?
Mhm.
And you also have a collection of available stones. And here I would look for something with greater than size 1,
Yeah.
because that tells us we can borrow from it, which
Yeah.
is exactly what we've done, right?
And so here, should I change this to instead be um, row of j minus 1 uh, uh, times, and so
I'll,
instead of putting the number in here,
mhm.
um, uh,
I'll say actually, yeah, save the actual cell itself.
yeah,
Yep, exactly. IJ. Perfect.
and so now I just have the spares and not
Mhm.
anything else. Okay. Yeah, I think that'll simplify it a little bit. Um,
Now,
all right.
I was gonna say you probably want to have as many spares. So in this case, because our permutation list can contain, we saw that entry where, there's one cell that can donate 3 times. So in this case, you can either use this approach. In my case, I would have used some other approach using, what do you call it? Using hash maps to optimize that further, but that's an optimization. A simpler approach will be add it however many times it can donate. That's
Yep.
the brute force approach that we can use here, right?
Yeah. Yeah, and that's what this is doing is it's going to loop
Mm.
through the available times and add
Mhm.
that to the array. And so ij will exist. If this was 3 here, then
I
ij will
see.
exist
Mhm.
twice.
Perfect. Oh, hence the -1. That certainly makes sense.
Yep.
All right. So from there, now you see, as soon as you're out of the loop, the next thing you can do there is use the function we have. So what you want to do is get all permutations. So in this case, you can, I don't know how, I genuinely don't know Ruby code actually,
No,
but
that's fine. Yeah.
what you wanna do is repeat this process here and say possible, what do you call it, solutions, possible solutions here,
Mhm.
and just get this off. So you're going to take that and then you're going to check for the possible permutations of what? In our case, we need of available stones against empty squares dot,
That length, yeah.
because that's our k, right?
Yep.
And we can even put that as a k here. Just say k equals whatever value we have here. Now with this, we can now evaluate the minimum distance. So if you come here and
Mm.
initiate this, and this can be, currently it's nil, but you can initiate this as a very large number, infinity. I don't know if it's a thing. Is there infinity in
Yeah,
Ruby?
there is, but you have to do
Mhm.
I think like float.infinity or int.infinity.
Makes sense. Yeah. Let's say, I don't know, float dot infinity. Okay, you know what? Let's just say it's infinity, or a million, or 99999, or whatever the number is. That's a very big number, that is. So that every number is smaller than it. Now, the question we need to ask ourselves here is, for each and every possible solution, so you loop through each possible solution
Mhm.
and evaluate the possible solutions against the empty squares, because the order of the empty squares is not going to change. You're going to keep it as is.
Yeah.
And it's our job to now just test out the different possible empty solutions that we have, empty squares that we have against the possible solutions that we have. And
Mhm.
for each of them, we're just going to compute the pairwise distances. So
Yep.
pick a number, pick another number, check for the absolute distance between them. And given that we've generated all permutations, we know for sure that we'll find one of them that has a minimum distance, like just the right combination of permutations.
Right.
You see where I'm going?
Yep.
Yeah. All right. You want to write that out?
Yeah. This here. Right. So I have the total number of moves. I have it here. So empty squares dot each. Um. So possible solutions. So there's a solution. So for each solution. Now this permutations syntax,
Mm-hmm.
it'll do 1, 2, and then there'll be a 2, 1. So it'll, or I'm sorry, so 1, 2, and 2, 3 here, and then there'll be a 2, 3, 1, 2 as
I'll say,
well.
how about we print it? Yeah, just try and print it and let's see. Given our example matrix there, let's see what it gives us.
Okay. Where is it?
Because one thing I like at least about doing these interviews is even if we are not able to like go pure interview mode, I like making sure that my candidates come out with one approach that they thoroughly understand.
Yep. P, min moves, min moves. Why is it saying min moves? I don't have that anywhere.
Min moves. Did I print something out? I do not think it's anywhere.
Okay. Yeah, now it's just an unexpected end of input. Oh, right here. Okay. So it's 0, 0, 0, 1.
Mm-hmm. All right. So what is that for us? Like, how useful is that for us?
So this is telling me that there's um, just 2 iterations possible.
All right. So let's even make it more complicated. We know that one example we talked about. So
Yeah.
let's do that. And then for the possible donor cells, let's make it that way. So what will that return? Let's just see how that looks like. That's good. So what is that giving us?
So it gives me 0, 0, 1, 0, and then there's a 1, 0, 0, 0. Okay. So it is flipping all of them around in every possible permutation of it.
Exactly. Now the question, let's go back to it. We have available stones. That's the locations of sections that can donate, and we can see 0, 0 can donate multiple times. Same case with I think it's a 0, 2, or is it? Not really sure which one it is. Although we do see it
0,
here.
yeah, 0, 1 can donate,
Mhm.
or sorry, 0, 0, 2 can donate multiple times, and no, that's not 0, 2, that's 2, 0. And then 2, 1 can
Yeah.
donate once.
Yeah. Although that's I cannot see examples that have 0, 2, and 0, 3. So I think we might have something wrong.
Hmm. Okay.
Do you see why
Yeah.
that's the case? Yeah.
Yeah, let's see. So available stones. Permutations of coordinates. Okay, available stones. I have this. And for every, if row j is greater than 1. Oh, that's why. Uh,
Hmm.
I replaced it with I here.
I see.
And so
Is it
that
K? Are we? What's our
ij.
K in this case?
Uh, yeah, because it's I, J, and inside J is
Hmm.
K. Yeah.
All right. Let's try that again. Let's make sure it works. Perfect. That
Yeah.
makes sense.
Okay.
That certainly makes sense to me. Okay. All right. So with that in mind, now we know we need to loop through both
Yep.
the I's and the possible solutions. I think, yep. So, take
So,
over and just, get the solution going.
okay. So possible solutions dot each, and so then I'll do each for each cell. I'm going to uh wait, not so I have empty squares. Empty squares is a flat array,
Hmm.
and so I should probably flip it around and do uh empty squares dot each. Do so, and then um
I was gonna suggest, given that you will be repeating the process with each empty cell in the empty square,
Mhm.
maybe we should have the same thing you have, like permutations, so the possible solutions. So for each solution,
Okay.
right? So I'm thinking, yeah, go on. Same thing you have exactly. And so once you're in here, so you're doing solution for each, but right here it should be simultaneous. So it should be both the solution as well as the empty square, because the size of solution here should be the same as the size of empty squares, right?
Got it. Okay.
Yeah.
Uh, and so then the solutions. Okay. So then I do 0 to
Okay, and you can still use k because you still have it there as a
oh,
variable.
okay. Yep. So and so then for each cell, all right.
Here we compute that distance, yeah.
So I should probably just make a method for cell distance
Hmm.
here.
Exactly, that's good.
Okay, and so I have cell distance. That should return the distance for each cell. And so distance plus equals cell distance. Um, uh, cell distance of possible.
Yeah.
No.
And that,
Uh, of solution and uh, empty squares. And then I say if distance
hmm
is less than total moves, then total moves equals distance, and then I return the total moves.
exactly. And I was gonna suggest at this stage, you remember that optimization we talked about? So if distance is greater than or equal to total moves, right? You immediately break. You don't need to keep going. That's one of the pruning things I was mentioning.
Oh, okay, got
As
it,
you do that loop, right?
got it. Okay, yeah, so I can do that. Uh, okay, okay, what doesn't it like? No imperial conversion of integer into array. Integer into array. What's so 10?
On line 58. Oh, it's that Manhattan distance computation that's giving us a problem.
Yeah.
You
Zero
can use both.
zero. Oh, I'm passing. Cell one is a pair. Okay. Yeah, I'm just passing it wrong. Um, so it'd be solution I. That's
Yeah.
okay. Distance. Oh, oh, okay.
You can use that too if you want. I provided some extra code down there
Where?
on line 64. It
Oh,
should be
okay.
the same thing, really. Yeah, only that I didn't
Y-
have like a description
yeah,
of distance.
yeah. It was my mistake was how I was calling it on line 115. I was passing it the set for the solution, not
Mm-hmm.
just the first or not just the I of the set. So I added this I.
Oh, I see.
Okay, it
All
still
right.
doesn't like distance. I've added distance here. So why doesn't it like distance? Yeah, that should see distance. Why? Oh, okay. Oh, this was an old error. I see. Oh, okay. 4. That's the answer. I have a put somewhere that I need to remove.
All right. So we have, I think that's actually the correct answer. So we're good on that. We can try with our original example here. We knew it is one here. You wanna try
Hmm.
that out, see if it works?
Yeah. 3.
Heck yeah, we got a 3. Good job. All right. So let's take a break at least from the interview mode. I know we've gone quite over in terms of like typical allocation for
Yeah.
time, but
Yeah. Thank you.
overall, yeah, overall, I'll say, you know, that it is totally okay because we kind of transition from interview mode into like helping each other looking to look through general permutations because they're a very common subset of questions to be asked, especially by Microsoft. In fact,
Hmm.
I'll say this has been the most popular question Microsoft has asked for coding interviews for the past 6 months.
Okay.
So you know, yeah, I want to start with you. So looking back at the interview, you can obviously identify areas where you think you did well and areas where you think you could improve on. So maybe run me through that. So what do you think you did well and what do you think you could improve on?
I think I'm pretty good at kind of communicating and just kind of walking through what the requirements are and
Mm-hmm.
identifying relatively early, where, issues and complexity is going to arise when looking at the problem. And so I feel like
Mm-hmm.
I was able to at least demonstrate that I can look at a question and see which parts of it are going to be easy, and which parts are going to be the ones where, it'll need more time. And I think
Mm-hmm.
that's about all I can say for what I did well. I think what I didn't do well was, finish the development in short order.
Mm-hmm. I'll say don't beat yourself up too much because you kind of, I think I mentioned this quite early, almost at minute 39. I immediately pointed out that there's usually two things I will be looking for. And this is where I need to also keep it honest with you. Not all interviewers will be looking for this, but sometimes you'll be lucky, you'll find an interviewer who has that intuition. There's a reason I work for interviewing.io because I'm kind of trained to look for more than just basic solution. I also
Mhm.
want to see the ability to think. In your case, I don't know, maybe I can just ask this randomly. Are you like from a standard CS background or like did you go to the SRE route?
No, yeah, like
through another path.
I don't have any kind of like formal CS training. I was I did
Hmm.
a few like Microsoft Access courses, things like that when I was in college. But
Hmm.
like it was just basic scripting. And then after that, I got more into the just SRE type DevOps work, which I've never been, what you would call a formal software developer, and never really did any class on
Hmm.
algorithms or anything like that.
And that's totally fine. That's where I tell people it's not about path that you used. At the end of the day, clearly there's also an element of thought. And by the way the solution has panned out, you can tell that you could kind of get there, but there's still some areas that were, not as apparent. But overall, you could easily see that you have the intuition as to how a human being should solve this. I
Hmm.
feel like that's usually the bit that most people fail to even communicate. And I'll tell you a secret. One thing I dislike about people who have a CS background is, and I'm one of them, so this is also something that I had to like give up myself. But because of the emphasis on some of these core terminologies, a lot of us forget to even explain what some of those are. Like you might hear me in an interview sometimes just say more distance or von Neumann distance or whatever it is, or BFS or DFS. You'll hear people throw these terms, and there's a benefit to it, but there's also a loss to it. The loss to it is if you don't have a background with some of this, it's over your head. You're like, what the heck is BFS? What the
Hmm.
heck is von Neumann? It just sounds like an abstraction. The benefit to it, though, is if you know what it means, it saves you 2 minutes of
Right.
having to explain what you're picking, what you're combining. You're just saying, I'm going to use BFS for this, rather than saying, I'm going to do a level by level neighbor exploration, of which I'll save all neighbors into an array, and then I'll look through each neighbor and evaluate them against. You just say it's BFS, and immediately somebody knows what you're saying.
Right.
Now, the reason I'm mentioning this to you is there's a benefit into there's a benefit to looking at some of this, and I'll keep it real. You probably won't see them at work too often, but they will eventually show up. Those are the fundamental terminologies and patterns. And if you look at a list such as Neetcode, let me share this with you. I don't know if you're familiar with Neetcode,
Yeah.
but if you're gonna do prep, you'll see that he has pretty much all the patterns covered. What he doesn't have is he doesn't have the structures and algorithms, listed out. So you'll see the patterns, but you will not see the structures at a high level. That said, if you were to go into actually, I am wrong. If you actually go into Netcode 150, he actually has them. You'll actually see them. The likes of backtracking, permutations, and all that. They're actually all there. So that's actually really good. He expanded it. So if you just look at the Netcode all list, you'll see everything you really need.
Okay.
So there's sliding window, there's the like of stacks, and let's see if I can find the one we've been looking at. I think it was under trees, and particularly we were looking at BFS and DFS. So that should be in traversals under trees. Do we have anything to do with that? I'm just checking it right now. Excellent. This is good. So if you look at I don't know, do you have the Netcode site open? If you can
Yeah,
open it, I'll
I
show you,
just
I'll tell you.
opened it. Yeah.
Yeah. So if you go into Netcode all and you look under trees, you'll actually see that he has maximum depth of a binary tree. I don't know if he has BFS and DFS, but it should be there. Breadth, let's see, breadth, such. Okay, he doesn't explicitly list it, but you can kind of see problems that would fall in that category. So, an example will be maximum depth of a binary tree. That immediately tells you DFS, depth
Hmm.
first search. And the reason I'm pointing this out is you can see how these terminologies come in handy to abstract a lot of logic that you'll otherwise have to explain from scratch.
Right.
Now, I would urge you to familiarize yourself with them. You don't have to do it from scratch right now because I imagine that your interviews are gonna approach soon, soon enough, and so you don't waste too much time going into the theoretics, but familiarize yourself with some of these terms. Unfortunately, and I'm not just throwing this in because I work for IIO. They actually have created a guide for us here. So if you actually look it up under the Learning Center, All these patterns are very in-depth articles, of which I was one of the writers, so I do know they were well explained.
Okay.
So this is an area I would highly recommend you look into because it will give you guides for pretty much all patterns you would ever need. And they actually also include a curated list of Microsoft specific questions. So it includes both the way the loop goes, but also questions that Microsoft commonly asked. Now, let's see. In terms of core feedback, you were right. Like your communication is spot on. I was able to easily follow everything you're saying. I really liked your line of questioning when it came to clarification, which was really good. Now, the one part I'll urge you to be mindful of is how long you spend on any particular section. With coding interviews, particularly, you want to, let's say, keep it less than 7 minutes with clarifications.
Mhm.
So that obviously means minimize, let's say, how much output you're writing, because sometimes that writing process is what takes up time. So you wanna
Right.
like quickly jot down summary points without really being overly exhausted. You wanna run through as many examples as you can, run through that clarification as fast as you can, and this only serves to help you because it maximizes how much time you have with the actual solution. And then there's something I like that you did. You are actually doing complexity analysis on the fly. Do that always because it saves you, especially since sometimes you don't have enough time at the end to actually do the complexity analysis. So what you did was actually really good, like analyze as you go or analyze as soon as you've identified a solution. But
Mhm.
that said, this preempts identifying the solution very clearly. So make sure even before you start to code, you've run the interviewer through what you want to do. Like you see what we did here, you can see what I did. I broke down the steps, and while this is extra detailed than I would normally write in an actual interview, this is kind of what I tend to do. So
Mhm.
write down the general steps of what you want to do before you jump into the code. And for me, I'll give you an example of how I'll do it. So I'll say, okay, so I've identified the problem here. We have multiple cells. We have multiple possible donors. So at the gist of it, I'm looking for combinations. So in this case, it's actually permutations. So I'm looking at palms of size empty. So this is what I'll say. So at a fundamental level, I'm looking of permutations of size empty that minimize minimize the Manhattan distance. That's what I'm looking for. Given that I'll be generating the permutations, then obviously uh, the minimum space complexity will be of size, palms, in this case, palms k, and under the assumption that all cells are empty except one, then this tells me that I'll basically be checking up all cells of size n, where n, and here I'll say n is equals to length times width, which is all cells. And if the interviewer wants to know the exact formula for permutations, I'll say I might not have it off of the top of my mind right now, but I know for sure it's a factorial. So there are
Mhm.
factorial possible permutations. Now, with this in mind, I know that the space complexity would also be n multiplied by n at each stage. So this tells me there are n empty cells, and all of them need to be compared against all other possible donors. So this tells me that this time complexity will be O of n to power 2. And you can think of it from a very holistic perspective where imagine half the cells are empty and half the cells are donors of just one cell. Then each cell has to pick one from another cell. So that tells me that we'll be scanning all cells against all other possible cells, and we'll do this n times. So it's actually n cubed. So it's n squared, although that's pairwise scanning, so it's technically still O of n, but it's n to power 2. And then this will be repeated. We get all the distances and we find the minimum. So this is space, and this is time. Now that said, I can potentially optimize this. So if I generate, so here I can say generate arms on the fly. So what I can do here is I can do the scanning as I generate them. So this means I can potentially optimize this to only require O of k. Actually, it's O of n, where n is the size as we defined it up there. So I can potentially optimize this even further so that I don't need n factorial. And what I mean by this is as I generate those permutations, I immediately test. Do you see where I'm going?
Yeah.
Yeah, and don't ever save. So this is what I'll do. And you can see that's exactly 4.5 minutes. So that's the description I'll use, 4.5 minutes, and then immediately start the solution. And this has gone even into analysis. It's gone into optimizations. It's also gone into the general solution. So if I told my interviewer that, and then I ask, are there any other does this, and here's actually another neat trick. You can always ask your interviewer, does this address the question you have, or do you want me to think more optimally? And the trick about this is if there's a better solution, typically your interview will tell you, can you think a bit more? And
Hmm.
so it helps you avoid going down a rabbit hole with a solution if there's a better one to think about. Make sense?
Yep.
All right. And let's see. Anything else other than that? Oh, I forgot to mention, and as you can see by the cases I'm throwing up here, they're edge cases you can think of, worst cases, best cases. So make sure you're also thinking about how those actually look like. So if you think the performance will be a certain complexity, make sure you're justifying it by giving an example off of the top of your head that would lead to that complexity. So you've seen an example here with me saying, if I was to optimize this to O of n, I'll basically generate on the fly. In this case, the worst case complexity will be where n over 2 cells are empty and all donors have only one cell. This is like the worst case complexity because it means each cell has to pick from at least one other and they're all different. So if you cite a particular complexity, make sure you also justify it with an example.
Hmm.
Does this make sense?
Yeah, yeah.
All right. But other than that, you have the fundamentals. So my general advice will be use the resources I've shared to go through these fundamentals. Try and, you don't have to master all of them. Frankly, it will take a while, but be familiar with the core terms so that you're not blindsided by any of them. Two, in this regard, make sure to also justify your complexities. Keep the communication strong. Minimize the amount of like time spent, especially on deliberation. Or if you're gonna spend a lot of time, make sure you like make it a bang for the buck by also doing analysis as you go and also proposing end-to-end solutions. Make sure you prompt your interviewer before starting to code so that tell them the solution you wanna go with and see if they are thinking of a better one before jumping in. This saves you a lot downstream. But other than that, keep practicing. Use the Leetcode list, use the IIO list that I just provided, and keep practicing because that's the only way we get better.
Yeah.
And at the end of the day, you clearly have the technical bits checked. You can code, which is good. The rest of it is all problem solving and familiarizing yourself with the core fundamentals in terms of terminologies. Okay?
Yeah. Um, so how far
Mm-hmm.
away am I, right? Because as I said, this is a
Mm-hmm.
level 63 interview. Um,
Mm-hmm.
and yeah, and so I, I don't know, like,
I'll, mhm.
yeah, go
I'll
ahead.
tell you this. So, one of the things about SRE interviews that I know about is they actually would probably give you an easier question than this. So,
Hmm.
that's one thing I know. Typically, it will be easier than this. So, that works in your favor. That said, I'm not going to sit here and lie to you. I still think you need a lot of practice.
Yeah.
If I was to give you an exact timeline under the assumption that you're actually crunching, solving about 5 questions a day, I would say you're probably a month off to cover
Hmm.
all the processes that you need. So if I were you on my interviews, let's say next week or the week after, I'll probably ask them to push it a bit further so that you practice a bit more. And I would say you probably could benefit from either dedicated coaching if you want to use the platform here. You can get a person like me curating a plan for you to just practice. They throw like a certain pattern of questions and you go through them. Alternatively, if you're okay with self-pacing, Leetcode is an excellent list. I would even invest in Leetcode Premium and solve the Microsoft questions. You don't have to solve all of them. I would say just solve as many mediums as you can. Definitely solve all the easies. If you just do that, which you can do within a month, it should get you there. And in terms of preparation, I would say use either the Learning Center here, which is free. The downside to the Learning Center is it's not necessarily a curriculum, but honestly, it should get you where you need. Educated.io is also a good resource, but honestly, I think the explanations on IIO are better. Like, we have engineers who actually interview you. They're giving you a perspective that is oriented towards an interview. So I'll just use this to build the fundamentals with the terminologies and then use those standardized lists to actually familiarize yourself. And I'll give you this spreadsheet that I really like, and you can use it as a self tracker for context. You can time yourself. You can, take notes to make sure you're actually knocking off all the patterns that you need. Does that address your question?
Yeah, no, thank you. Thank you for that feedback. Um, yeah, I've been doing a lot of what's
Mhm.
the site that I've been doing? Uh, have you heard of Code Signal?
Yes, I do know Code Signal. I hate it, but I hate it because it always gets me. But I definitely appreciate what it does.
Okay,
Like
like
I've
is
gotten
that
a lot of Code Signal interviews. So
is
it's
that
a
a
fair resource too. Like,
so like yeah,
yep,
because I've
it
been
is.
doing that. Like if I just keep doing that, or should I
Mhm.
switch to Neat Code or Leet Code,
Mhm.
in your opinion?
In my opinion, I'll use both because there's nothing preventing you from doing it. That
Hmm.
said, the one benefit to LeetCode and NeetCode is one, NeetCode is actually based off of LeetCode, so using one or the other, pretty much the same. The
Okay.
one benefit is interviewers are lazy as heck. They're not going to come up with new questions,
Okay.
which means you're more likely to get a lead code question than you are to get a code signal question in the actual interview. So using lead code, especially if you have the premium account,
Hmm.
trust me, you will be surprised. Like, I'll give you a quick tip for meta interviews. All the questions I was asked were lead code questions, all
Okay.
of them. And keep that in mind. Those are 4 interviews, 2 questions each, 8 questions, and all of them were on lead code. I was stunned.
Okay.
All
All
right.
right. Yeah, we got work to do.
Absolutely, and don't take this in any way. Don't take it hard or anything like that. Because I feel like that's the one key thing to make sure you get out of a mock interview. In a mock interview, if you perform too well, it was probably useless. You're already good.
Right.
If you struggled, good. That's the purpose of it. You needed to iron out your weaknesses. So in this case, we've identified them, work on them, get other mock interviews. In fact, a quick tip I'll even give you is conduct mock interviews yourself. See what other people are failing at.
Hmm.
Build that instinct to see what the interviewer could be looking for in you. It doesn't have to be company oriented. Just watch other people solve and see what they're doing, where they're messing up, and then learn from it.
Yeah.
Sometimes the best lessons you can gain are from watching others do the same thing. But keep the practice going and you're going to do well, okay?
Okay. Thank you so much.
Absolutely. All right, man. I hope you enjoyed this and yeah, have a good evening.
Yeah, you too.